menang nek wong tuwa. Tapi dudu nabi.
Belum gabung ya, Mas Adi ya?
Sepertinya daring, Pak. Sebentar, mungkin kita tunggu sebentar lagi.
Saya nggak punya, cuma saya email, tapi dia nggak tahu apakah respon atau enggak.
Kalau jam 9 di sini, di sana jam berapa?
Nah, ya itu. Mungkin jam
Di sana harusnya
10 atau
11.
jam
11 mungkin. Selisih 2 jam kalau nggak salah ya, Pak.
Duluan sana. Sama dengan Jepang ya?
Iya, sepertinya. Tapi kemarin sudah kita kan Pak, jamnya
Sudah
dikasih keterangan GMT plus 7, jadi mungkin sudah menyesuaikan.
Artinya kan di Jakarta toh?
Oke. Jadi
jangan-jangan nah, nggak tahu. Di jadwalnya kan anu toh tetap anu kok di
Ini link Zoom-nya sebagian saya share di YouTube aja kali ya Pak ya, agar ini karena pesertanya juga baru sedikit. Kemarin sebenarnya yang daftar untuk mahasiswa kan di atas 100, jadi untuk yang di YouTube belum saya share langsung aja mungkin ya Pak, agar beberapa masuk ke sini saja.
Atau nanti aja kalau sudah anu Pak.
Oh nggih.
Jangan-jangan
ini mahasiswa juga baru pada masuk sepertinya. Oh ini sudah masuk Pak Prof Jeon. Sudah sebentar. Ya, sudah masuk.
Hello.
Hello, good morning, Prof.
Yeah, good morning.
How are you?
Good. How are you today?
Good. Yeah, fine. Thank you. The connection is okay for you?
Yeah, connection is very good and sound is
Very good.
clear.
Okay. Thank you for your join this. You have become
Thank you.
Speaker today.
Yeah, I'm really happy to have a chance to present my research in your department.
Yeah. Okay, I heard I checked your profile in the internet that you are in Alabama University. Is correct?
Yes. Yeah, that's right.
I see. Yeah. So you from Alabama and then come back to South Korea.
Yeah.
That's right.
Yes. And then after I finished the PhD in Texas A&M University, I was the postdoc at Georgia Tech for 2 years, and I was the assistant professor at the University of Alabama, USA.
Yes.
For another 2 years, and then I moved back to Korea, and then it's been already 2 years here also.
I see. Yeah. But you are very productive in producing the publication.
Okay, thank you.
Yeah, I just saw I see your profile in Google Scholar and also in Scopus. But in Scopus, I'm a little bit confusing because only one publication in your profile coming from Kookmin University. But all are mostly from Alabama. Yeah, in the institution.
Yeah, but
Alabama.
most of the paper is published after I joined the Cumin University. So.
Yeah. Yeah.
Not a problem.
Yeah, no problem.
Mm-hmm.
Okay. I think this is time for starting the seminar. Pak Agus have already prepared it's okay. Yeah, every day. Okay. yeah, we would like to start our
Yes.
seminar. Yeah.
Sure.
Okay.
Yeah, I will share my screen.
Yeah.
And
Or you want
then-
to okay, before start your presentation, maybe I would like to introduce my head of department and to the participant. And right now we have more than 100 participants from our student and also the alumni of our student, and also from outside. I think it's more than I'm not sure, but I think right now still 37 participants. But outside of this Zoom, we connected to the YouTube and also streaming. I mean that more than maybe more than 100 participants join in this seminar. I think this is the and before you present your expert and your topic, please Dr. Agus Kuncoko to give opening remarks, maybe 2 or 3 minutes, just to say hello and also speak what Pak Agus would like to say. Please, Pak Agus.
Yeah, thank you very much, Professor Nuryono, as a moderator in online Studium Generale. Today's first of all, I would like to thank you very much, Professor Jeon. Excuse me, I would like to introduce myself. I am head of chemistry department, and thank you very much for your willingness to become a speaker in our online Studium Generale. And also the honorable, all of the participants, both in the Zoom and the YouTube online. On behalf of Department of Chemistry, we are very glad to welcome you to introduce electrochemical active nanomatter for energy application in our Studium Generale, and I do hope that after your speaking, the discussion will fruitful for the advancement of the science and technology. And I congratulate for this seminar and enjoy the online Studium Generale. And thank you, Pak Nuryono. Thank you very much. Yeah.
You are welcome, Pak Agus Kuncoko. Dr. Agus Kuncoko has already give opening remarks on this seminar, Studium Generale, presented by Prof. Jeon. Sorry, maybe my pronounce is not so correct.
It's very close.
Okay. Yeah. Okay. Very close. Thank you.
Okay.
Okay. Yeah. I think this is your time to present your topic, talking about electrochemical active nanomaterial for energy application. I think most or a lot of us are interested in this topic, especially we have a research group so-called material chemistry. It means that some of us are interested, and also maybe there are correlation, good correlation between nanomaterial and also material that are developed in our department. hopefully this is very useful and also can be continue in the next future on the collaboration on something like that, and also maybe some of our students would like to join your laboratory to do research and also any kind of the collaboration. I think maybe before, yeah, I think it is your time, and please you present your topic. The time, I think, yeah, one hour, and then after that we could come to the discussion. Please,
Okay.
Professor Jeon.
Okay, thank you for the introduction, and I am very pleased to have a chance to communicate with you, also give a presentation about my previous research and current research. So my name is Jeon, the assistant professor at the Department of Applied Chemistry in Kookmin University, placed in the Seoul, South Korea. So today I would like to present the electrochemically active nanomaterials for the energy applications. So before begin, I'm gonna introduce the Kookmin University that I'm working at right now. So Kookmin University is the one of the research-oriented university that is located in the Seoul. Is the capital of the South Korea. So this is the picture of the Seoul at night. And the university, the Kookmin University, is found actually 1946. It's been already, I mean, 70, almost 70, 60, 70 years. And this is the one of the oldest the private universities in South Korea. And the Kookmin University is ranked the first for the technology transfer in South Korea. This is 2018. And then the first, ranked first also for the entrepreneurship education in South Korea. And total enrollment is around 19,000 students as of 2018, and our department has the almost 300 students. And then my lab, laboratory title is the Functional Energy Materials Laboratory, so-called FEML. The research area is about the conducting polymer and the functional polymer like self-healing materials and carbonaceous material, and also electrochemical energy storage and conversion. So now I am actively looking for the multiple graduate student candidate who is interested in the research field. So we welcome the candidates who are willing to work in a team and highly motivated and curious and passionate student. So these are the benefits if the student can join as a graduate student in my group. So full the tuition support will be provided, amount like almost 6 million won per semester will be fully covered, and living allowance and monthly stipend corresponding to the 900,000 won per month will also be provided, and on-campus dormitory fee deduction will be also provided up to 50%. So if you are interested in joining the group, or if you are interested in communicating with me for the possible the opportunities, you can contact me through the email directly. And today I would like to talk about the two different research topics. So first one is the conducting polymer-based electrode with high stability for the energy storage. So usually the conducting polymer has the low electrochemical stabilities, especially the polyaniline. So in order to enhance the electrochemical stabilities, I suggest the two different approaches, the template polymerization and layer by layer assembly method. In the second part, I will talk about the electrically controllable plasmonic behavior. Specifically, I will talk about the core shell nanostructures consisting of the gold nanocube core and conducting polymer, the polyaniline shell. So let's start the first the part of my presentation, which is about the charge storage in polyethylene-based electrode materials for the energy storage applications. So this is the brief background for the energy storage systems. So energy storage systems can be classified into the three different the categories. The first one is the battery and capacitors, conventional capacitors, and electrochemical capacitors. So this Ragone plot shows is energy storage performance of the each energy storage device in terms of the specific energy and specific power. So specific energy means how much charge can be stored and how much energy can be obtained by the energy storage device. And specific power means how fast we can deliver this kind of energy. So as you can see, battery has the high energy, but the power is less than the other energy storage device. And conventional capacitor has very high power, but its energy is quite low. And electrochemical capacitor or supercapacitor is placed in between. It has the intermediate energy and intermediate power. So batteries has the high specific energy. So these days, battery is the most widely used energy storage device in the cell phone or laptop, and even in the large-scale electrical grid. For example, this is the laptop battery, and this like big like scale one is also the battery, the pack that is directly connected to the solar cell. In the daytime, the energy can be light, is converted to the electricity by the solar cell, and the converted energy, converted electricity can be stored in the battery pack. So basically, it is the combination of the large-scale grid electrical the energy storage and conversion system. So lithium ion battery was invented by the Sony company in 1991, so almost 30 years ago. And then since that time, the battery performance is continuously increasing by the materials development or like manufacturing, the engineering. So why lithium-ion battery is the most widely used one? Because it has the low standard electrode potential, around -3 volts. This electrode potential is quite low, which means this kind of lithium is easily oxidized, and then we can get the high amount of the voltage. And this voltage is directly proportional to the Gibbs-free energy change. So which means if we have the large voltage, we can obtain the high energy. And then lithium also has the very lightweight. Atomic number of the lithium is only 3. So atomic mass is very small. So we can obtain a lot of energy in the same mass as compared to the other materials. So the general component, usual component of the lithium ion, the battery is like this. The cathode material usually the lithium cobalt oxide based the material is used with a polymer binder like PVDF binder and conductive carbon black. And anode, the graphite with the binder is used, and separator, polypropylene and polyethylene porous structure, and electrolyte lithium salt in the carbonate-based solvent. So the battery can be fabricated in various like configurations like cylindrical, prismatic, coin, and flat type. And when you design the battery, we need to consider the several different factors and properties such as energy density. So it is very important how much energy we can obtain, the maximum energy density we want to obtain. And power is also important. So we want to deliver the energy very quickly. So the power is another the very important factor. And cycle life is also very important. If it has the very short cycle life, even though it has high energy and high power, it is usually not very it doesn't have a high impact because the battery cell will be die very quickly. So we want to use it for a long time. And cost is another the factors that we need to consider. And safety is also very important. So these are the general chemical reactions for the lithium cobalt oxide based lithium ion battery. So for the discharge process, this kind of lithium cobalt oxide is obtaining the lithium ions and electrons and convert it to the lithium cobalt oxide. Actually, the intercalation reaction is taking place in the cathode. And at the anode side, the graphite is losing the electron and losing the lithium ions at the same time. So this kind of electron from the graphite anode is transported to the cathode. And this lithium ion is also transported throughout the electrolyte and then intercalated into the cathode during the discharge process. And charge process is completely opposite. The cathode is oxidized and anode is reduced, and overall reaction is here. So in the charge process, lithium ion is migrated from the cathode to an anode in the charge process. And this is some of the characteristics of the lithium ion battery. Specific capacity can be calculated in this formula, and specific cell capacity and specific energy and power all can be calculated in by the well-known formula. And coulombic efficiency also the important factors. And C rate is the sum of the current rate that you want to use. Okay, these are some of the candidate electrode materials for the lithium ion battery. The x-axis is the capacity and y-axis is the potential versus lithium. So if it has the high potential around 4 volt, higher than 3 volt, which means it can be used as a cathode material. And if the redox potential is low, like less than 1 volt or less than 2 volt, which means it can be used as an anode material. So for example, if you use the lithium cobalt oxide as a cathode, and if you use the graphite as an anode, you can obtain the cell voltage around 3.8 volt or around 4 volt. And electrolyte, usually some of the carbonate-based electrolyte is generally used. And if you take a look at the cost structure of the lithium-ion battery, so most of the cost is coming from the cathode material. It occupies 25% of the overall cost, which means cathode material is quite expensive. And anode material occupies only 8% of the cost structure. And current collector, electrolyte separator takes small portion of the cost. And land cost, labor fee, and engineering fee and system fee also takes lots of the overall cost. So it is very important to decrease the cost of the cathode material because inorganic material itself has the high cost. So we want to actually lower the cost by using the different the organic-based electrode materials. So there are several different kinds of electrode materials we can use. These are the all organic-based electroactive materials. So first one is the conjugated hydrocarbons. So this one has the conducting polymer like this kind of structure, and conjugated amine. These are also the conducting polymer like the penny and polypyrrole. And conjugated thioether also can store the charge like polythiophane-based polymer. And disulfide also can store the charge, and thioether. And also the radical polymer also can store the charge, and conjugated carbonyl can store the charge. It has a lot of advantages such as low cost, and its redox potential range is roughly between 2 to 4 volt, which means it can be used as a cathode. And some of the also organic electroactive material also can be used as an anode. And synthetic tailorability is also the big one by introducing the pendant group or by controlling the molecular structure of the polymer backbone. We can control the redox potential. But most of the problem is coming from the low electrochemical stabilities, which means if you charge and discharge several times each, the capacity fade very quickly. So the typical conducting polymer has the high theoretical capacity and lots of advantages like high cost and high theoretical capacity and synthetic tailorability and mechanical versatility. But as I mentioned earlier, the biggest challenge is that this low cycling stabilities. So polyethylene is the also very well-known conducting polymer family. And polyethylene can exist in this kind of 5 different forms, and Lucca emeraldine base is the fully reduced form of the penny, and this phenylene state is the fully oxidized form of the polyethylene. And emeraldine state also exists in between, like fully oxidized phenylene and fully reduced Lucca emeraldine form. And this the emeraldine and phenylene form can exist in the base form or salt form depending on the chemical environment. So this polyethylene can be applied in various applications such as sensors, memory device, and energy storage systems. These are the advantages, and it also can have very high conductivities, sometimes up to 10 Zeeman per centimeter. But its problem is it has very short cycle life because of the irreversible oxidation to the phenylene base. So our question is, how can we enhance this kind of cycle life? So we suggest the 2 different approach. The first one is the template polymerization and layer by layer assembly. So by using the first approach, so we adopt the template polymerization and synthesize the polyethylene doped by the polyacid, that is poly-2-acrylamide 2-methyl 1-propane sulfonic acid, so-called the PEMSA. It has the sulfonic acid group and it has the amide group in the functional pendant group. And this kind of polymer complex has the good processability in water because of the excessive sulfonic acid group coming from the PEMSA. And its conductivity is known as like around 1 Zeeman per centimeter. And it shows the quite stable redox property in the water up to pH 9. So we can expect there should be some kind of strong, attractive charge-charge interaction between the protonated amine and deprotonated negatively charged sulfonic acid group. So our hypothesis is that maybe this kind of charge-charge interaction can enhance the cycle life and cycling stability for the energy storage. So first we synthesize the penny-PEMSA using the template polymerization, and then we test it in the 3 electrode cell as well as 2 electrode cell in the oxygen-free and water-free argon-filled globe box. And we adopt the cyclic voltammetry and galvanostatic charge-discharge measurement. So in the cyclic voltammetry, these are the methods. So we linearly increase the voltage and linearly decrease the voltage and observe the current response in the each voltage. So when you increase the voltage, there should be the oxidation reaction, which is called the anodic scan. And if you decrease the voltage, there should be the reduction reaction, and which corresponds to the cathodic scan. So we observe the 2 peaks from the 1.5 to 4.5 volt of the penny PEMSA, which means 2 different reactions is taking place in this potential range. So we measure the capacity based on the mass of the polyethylene alone. So polyethylene has the capacity around 100, but penny PEMSA has the capacity around 240 milliampere hour per gram of the penny. But if we convert this kind of capacity based on the penny PEMSA polyelectrode, this capacity is 61, which is smaller than the polyethylene homopolymer electrode. And maybe this is the most important data in the first part. So in the case of the polyethylene homopolymer, its capacity decreased very quickly from the 100. it died after 100 cycle. Its capacity almost zero. But in the case of PEMSA, its initial capacity maintained very well. The almost original capacity may be more than 85% of the original capacity is maintained even after 800 cycling. So in order to find the reason why we have the very high electrochemical stabilities for the PEMSA, so we actually performed the UV spectroscopy for the PEMSA and polyethylene homopolymer before and after the cycling. So before cycling, the PEMSA can exist in the LB, ES, and PS form, depending on the electrochemical voltage applied. But after the cycling, it can also show the reversible behavior. It exists ES, PS, and LB, depending on the electrochemical potential, which means even after cycling, this PEMSA is still reactive. But in the case of the penny homopolymer, you can change its oxidation state before the cycling, but after the cycling, it just exists in the polyethylene base form instead of just changing its oxidation state, which means this polyethylene is not active anymore. So these are the reaction scheme of the PEMSA and polyethylene. So polyethylene and PEMSA can utilize this kind of reaction. Actually, between leucoamide base and emerald salt. If you increase the voltage, this leucoamide base is converted to the emerald salt, and then after beyond the 3.5 volts, this kind of polyethylene is irreversibly converted to the polyethylene base by losing the proton here and losing the electron, and it cannot be converted back to the emerald salt form because there is no available proton in the electrolyte, so it cannot be converted back to the emerald salt form. But in the case of the PEMSA complex, actually there is a strong interaction between the protonated amine group and sulfonic acid group, and there is no loss of the proton, so it can be reversibly switched between emerald salt and polyethylene salt, even at a very high voltage like 4.5 volt versus lithium. And second approach we use is the layer by layer assembly. So layer by layer assembly is the very simple and effective and inexpensive method to fabricate the multi-layer films. So if you have the charged substrate, you can immerse into the solution which contains the oppositely charged species like the negatively charged species. This species can be polymer or metal oxide or can be anything. And then there will be the charge attraction, and this negatively charged species can be adsorbed onto the positively charged substrate. And then you can repeat, and then you can immerse it into the another solution which contains the positively charged species, and then there will be another adsorption process. And then if you repeat this kind of process, actually you can build up the multi-layer, the films on top of the substrate. And thickness can be easily controlled, and the film property also can be controlled by changing the solution pH and ionic strength. So in the first part, we use the template polymerization method to fabricate the PEMSA electrode. But if we just use the layer by layer assembly techniques, so we are wondering that this kind of similar PEMSA multi-layer films can have the same enhanced electrochemical stability or not. So to answer this kind of question, we build up the three different layer by layer the films. So these are the cations that we polycations that we used, and these are the chemical structures of the polyanion that we used, and we repeat this kind of LBL the process and build up these three different multi-layer films. And then as you can see, the film became darker and darker with the increasing number of layer pairs, which means actually the film is growing very well. And these are the growth profile of the LBL films. And then penny-PEMSA and penny-PEMSA has the highest the capacity higher than the LPI penny-PEMSA because of the high the conductive the polyethylene content. But the LPI penny-PEMSA has very low capacity. And these are the cycling stability. So the penny-PEMSA boost its cycling stability. So when you cycle it between 1.5 to 3.5 volt, this penny-PEMSA capacity gradually decrease. But if we perform the elevator assembly with the penny and penny-PEMSA, the decrease rate is much slower as compared to this one. And then this LPI penny-PEMSA shows the highest electrochemical stability. So it just showed the very stable electrochemical property during the cycling, but its capacity itself is not really high. So we perform, okay, how about the other polyelectrolyte instead of the PEMSA? So we perform, okay, the elevator assembly using the different polyelectrolyte, like the polyacrylic acid, PAA, which has the higher pKa than the PEMSA. So its pKa is around 6.5. And in this case, instead of the the traditional conventional deep assisted elevator assembly, we perform the spray assisted elevator assembly because of these advantages. So deep assisted elevator assembly is usually very slow and possible cross contamination. And if you have the large substrate, it is very difficult to dip the very large substrate into the large scale solution. But in the case of spray assisted elevator assembly, its processing time is very fast. So it only takes 3 minutes per layer pairs, and no concerns about the cross contamination, and easy to scale up because there is no direct contact between the solution and substrate. So we perform this kind of spray assisted elevator assembly, and we first synthesize the polyethylene nanofiber and polyethylene dispersion and use the spray assisted elevator assembly. And then growth profile is obtained, and after maybe 50 number of layer pairs, we can build up 6 micrometer film for the polyethylene nanofiber and PAA with a high molecular weight and low pH. We also control the molecular weight of the PAA and the pH of the PAA. So these are the capacities. So polyethylene nanofiber has the highest capacity, around 150. But other LBL electrode has the little bit lower the capacity than the polyethylene homopolymer. But during the cycling test, from the 1.5 to 4.2 volt, its capacity, the polyethylene homopolymer capacity gradually decreased, and after 500 cycles, its capacity just 0. But in the case of penny-PEMSA, the capacity degradation rate is much slower, and especially the polyethylene and PAA regular the morphology, the capacity increased very quickly after during the 100 cycling, and then it maintains. And even after 1,000 cycling, it shows the very stable the performance. And the quick summary is, in the first part, we successfully adapt the LBL assembly and template polymerization to enhance its cycling stability. In the second part, I will introduce the electrically tunable plasmonic behavior of the gold and electroactive polymer nanohybrid. So these are the publication about these topics. So research background is actually when the light is irradiated into the metallic nanostructures, which has the much smaller than the incident light wavelengths. Actually, there is a collective oscillation of the free electron in the metallic structure, and the light is basically the electromagnetic wave. So electromagnetic field is interacting with the electron cloud in the metal. And this kind of frequency of the collective oscillation is called the localized surface plasmon resonance, in short LSPR. And this LSPR property strongly depends on the metal size and metal shape and composition of the metal, and also the surrounding dielectric, the environment. So the below is the equation that can relate the LSPR peak position, peak wavelengths, and refractive index of the surrounding medium. And this is an example of the golden nanoparticle. If the golden nanoparticle is sphere, its color is pink, and the LSPR peak is appeared around the 530 nanometer. But if you synthesize the golden nanorod, and the color is changed depending on the aspect ratio. So there is another longitudinal LSPR property is emerging, and it shows the very sharp and very strong longitudinal the LSPR peak property. So this LSPR actually can be utilized in the various applications, including solar cell photocatalysis and sensors and biological imaging. So for example, these plasmonic sensors were realized to detect the Alzheimer's disease. So in this case, the silver array decorated with the ligand with the specific chemicals, and consequently this plasmonic nanostructure could detect a existence of the specific chemicals based on the LSPR shift, because there should be interaction between the ligand and chemicals, and then the changed environment can give the different LSPR position of the nanostructure. So based on the LSPR peak shift, we can identify the existence of the specific chemicals. And to some degree, we can also know the concentration of the specific chemicals. And another example is the tunable lasing system with the gold nano array. And by using the gold nano array, with several different liquid gain here, and it was possible to tune the lattice plasmon resonance, and also can modulate the emission property of the laser. So we can control the color just by providing the medium. So it is possible to synthesize the various plasmonic structures with the specific LSPR properties through well-defined synthesis technique. However, for a given structure, it is difficult to change the LSPR property in reversible manners, and responsive plasmonic systems can make it possible to modulate the LSPR property in real time. And the responsive plasmonic systems can be realized by using the various stimuli such as pH, temperature, light, ionic strength, and electrical potential. And our group previously demonstrate the plasmonic systems by changing the pH and the light. So in this case, the pH responsive, the PAA, the polymer, was employed as a matrix to vary the interparticle distance between the silver nanowire and gold nanoparticle. And as a result, the on-off source property can be obtained by simply changing the pH value. And we also report the light responsive plasmonic systems composed of the silver nanocube and light responsive the azopas molecule. And by irradiating the light, the reversible, the light-induced photoisomerization takes place, resulting in the refractive index change in the light-responsive azopas molecules. So as a result, the LSPR position of the gold nanocube can be reversibly tuned. So electrically tunable plasmonic systems is another the responsive plasmonic systems, whose property can be controlled by the electrochemical potential. The concept of this is to combine the electrochromic polymers and plasmonic nanoparticles to obtain the real-time LSPR control. So the electrochromic polymer can change its oxidation state when chemical potential is applied. And the processability and colors of this material can be controlled by modifying the backbone and its side chain. So previously, we demonstrated electrically tunable plasmonic systems using silver nanocube and water-soluble blue electrochromic polymer. And this water-soluble ECP blue was used as a responsive matrix, and its refractive index was controlled by applying the electrical potential. And as a result of this refractive index change, the NSPR peaks of the monomer and dimer can be reversibly modulated here. So in this study, we particularly interested in the core shell nanostructures for a real-time control of the NSPR property. So because of its advantages over the conventional layered structure. So in the conventional layered structure that was published before, and it is difficult to control the plasmonic coupling. So if there's the plasmonic nanoparticle touching each other, the original plasmonic property is disappear, and the aggregated NSPR property will emerge. So it is generally very difficult to control the polymer thickness in nanoscale, which means if you want to control the thickness like 5 nanometer, 10 nanometer scale, it is very difficult to control in that the accuracy. So it is not the ideal system to study the effect of the film thickness of the NSPR. So, but in the case of the core shell nanostructures, this kind of shell can prevent the undesirable plasmonic coupling, and this shell also can act as an electroactive media as well as the physical spacer and provide the different refractive index environment to the gold nanocube. And intimate contact between the core and shell was also guaranteed because the core shell nanostructure, the interaction between core and shell is very strong. So the reason why we use the gold nanocube instead of the nanosphere is because it's high sensitivity, high refractive index sensitivity than the gold nanosphere. So first we synthesize the gold nanocube through the established seed-mediated method, and then by applying the oxidative polymerization, we could successfully synthesize the gold nanocube and the polyethylene shell with the 30 nanometer, the penny shell. And we can also control the shell thickness in nanometer scale, like just simply by repeating the polymerization process. So after polymerization process, a 30 nanometer shell was formed, and then if you repeat the same polymerization one more time, and the film thickness is now the 18 nanometer, and then we can control it to 26 nanometer and 37 nanometer. And these are the SEM image of the gold nanocube and penny with 37 nanometer shell thickness. So these are the shell thickness as a function of number of polymerization cycle. So this is the UVB spectrum, and now the color is different because of the existence of the shell. And then we coat the conductive ITO substrate with the polyethylene, the penny quotient nanostructures using the 26 nanometer shell. And then we can find some of the monomer and dimer, and the height profile was also characterized. And then when we apply the electrical potential, we can expect the reaction between emeraldine base and emeraldine salt. So these are the refractive index obtained by the ellipsometry, and we can expect the redshift when we convert this emeraldine salt to the leucoemeraldine base because of this kind of relationship. So as expected, when we decrease the electrical potential and convert the emeraldine salt to the leucoemeraldine base, this NSPR property is redshifted as expected. So we can control the plasmonic peak position, like from 555 to 535. So 20 nanometer LSPR peak modulation is possible in this kind of gold nanocube and polyaniline shell. And we can also modulate it continuously multiple times. So there is no kind of significant peak change when you apply high voltage and low voltage. So it can show the very reversible behavior. And even after 100 cycles, it shows the very similar cyclic voltammogram. And plasmonic peak position remained the same without any kind of shift. So we also study the effect of the penny shell thickness on the plasmonic the properties. So maybe this graph, the LSPR shift is increased depending on the thickness of the penny shell. But after the sum of the threshold penny shell thickness, it is not a significant increase in the LSPR modulation, which means the LSPR, the sensitivity is only LSPR gold nanocube is only detect the environmental change around the 25 nanometer region. So these are the FM image of the gold nanocube and gold nanocube penny, the quotient structures. And we also performed the single particle studies for the quotient nanostructures. So for the AFM, we found the one particle, just monomer, one particle. And this number 2 is the two particles contacting each other. And these are the height profile of the one monomer and two dimer. And by using the different method, hyperspectral image, so we try to find the exactly same spot. So this is the L shape, and we successfully found the L shape, and this is the arrow shape, and we found the arrow shape. And this monomer corresponding this one, this dimer is corresponding to this one, and these are also the same shape. So we convert the ES to the LB for the monomer and dimer, and it shows the exactly very similar position, which means this kind of aggregation is not affecting the LSPR property because of the penny act as a physical spacer to successfully prevent the LSPR, the coupling. So Fttd simulation was also performed, and the experimental experimental result is follows with the theoretical the LSPR shift. And after that, we also demonstrate the dual responsive golden nanode and penny, the quotient nanostructures. So in this case, we use the two different stimuli. The first one is the electrical potential, and second one is the pH change. So we convert this LB to ES and ES to PB, and then refractive index is very high. Refractive index change is very high when the ES form is changed to the PB form. So these are the TM image of the golden nanode and the polyaniline. And with the only 8 nanometer penny shell, we can control the 100 nanometer LSPR peak position, which means with the very small amount of the polyaniline, we can easily control and we can obtain the large modulation of the LSPR property. So this paper is separately published in the Chemistry of Materials too. The other research I perform is the MAF-derived porous carbon and other polyaniline-based electrode and electric field-induced morphological transition, and lignin-based sustainable porous carbon and polysilicon-based conjugated polymer electrode too. So very recently, we published the self-healing and stretchable thermoelectric materials in the energy and environmental science, which has the impact factor 33. And I would like to show you some of the video about the self-healing materials. So we successfully synthesized this kind of self-healing polymers, which is stretchable, highly stretchable. It can be stretched up to the 750%. And then after cutting it, the light is now off because electrical connection is now off. And just by contacting each other, it starts to self-heal. And then by applying the gentle press, so it is self-healing completely. And then it shows the very stable electrical conduction. And it can be stretched 100%, even 300% strain. So these are the thermoelectric performance of this material. And also this is another video to show the self-healing features. So we made a cut, and then this kind of cut is a self-healed as time goes by. This scratch is completely healed, like zip up. And then after 5 minutes, it's completely healed. So this is the slow video. So it just shows the self-healing. And then these are my research the area. I'm using some of the functional material, like functional conducting polymer and metal organic frameworks and graphene oxide, and adapt the electrochemistry and alveolar assembly and other synthesis method for the energy and energy storage and energy conversion. So now I am focusing on the thermoelectric material and some of the lithium ion battery using this kind of the concept. So we are seeking the multiple the candidate for the MS PhD integrated program and PhD position. So if you are interested in joining the group, and please contact me. And as I mentioned, this is the benefit of the program in my group. And tuition fee approximately 5.5 million won per semester will be covered, and living allowance monthly stipend corresponding 900,000 won will be given per month, and on-campus dormitory fee will be deducted. So my lab equipment has the glow box, and this is my lab hood and electrospinning and some of the oven and profilometry microscope, potentiostat, FTIR, and thermal evaporator, and crimping machine and student office. And now I'm working with the yoga graduate student in Indonesia student, and also the GCO, the postdoctor in my group. So thank you for your attention today. And this is my email address. So if you have any question about the opportunity, you can also contact me directly. And thank you for your attention. So if you have any question, I would like to answer the question from the audience.
Professor Noriono, please dismute your computer.
Sorry. Yeah.
Yeah.
Okay. Thank you very much for Professor Jeon for your nice and also interesting presentation. And now we go to the discussion. I think some of our participants have already prepared the question, and you can answer and also give a response. From the chat menu, I think who won a question?
Okay.
Yeah, Vini Olivia. Maybe you can speak I give you time for you to directly give a question for Professor Jeon. Please, Alivia, Winnie.
Okay, thank you.
Yeah.
Yes. Does my voice clear? Okay.
Yes.
Thank you. Thank you for such an interesting presentation. My name is Vinny, and I think and I do hope that you will not mind to address several questions of mine. I think for the first question, I noticed that during the synthesis process on the template polymerization, thus the chemical system is prone to oxidation. We often use a glove box when we want an inert situation of our chemical system. I just want to confirm: is it critical to synthesize the material?
Yes, so if you really control the conductivity, some people use the inert condition. But yeah, in this case, I also use the nitrogen condition. But instead of the glow box, I just use the nitrogen gas and then purge the reaction vessel in the nitrogen gas. So just to remove the oxygen, so oxygen can actually participate and then decrease the conductivity of the conducting polymer. So I just purge with the nitrogen to make it inert the environment. But I think maybe if you just want to get some certain degree of conductivity, maybe I think you can do it in the just air condition.
Okay, all right, thank you. And for my second question, is it possible that the mechanism interaction between of PANI, PM, PSA caused by intermolecular interaction among dependents? I mean, you use sulfonic acid as dependents.
Right. Yes. So interaction is usually the charge attractive interaction, charge interaction, and cross-linking possible, but not really. I think this kind of charge interaction is more like dynamic instead of just fixed interaction, because it is not the covalent bonding. But somehow, if you have a lot of like molecules, it can cross-link. But I think in this case, is more like the charge attraction, just dynamic attraction instead of the cross-linking. But I think it is also possible to have the cross-linking. But what I'm saying is just mostly the dynamic the interaction instead of the cross-linking, when I just see the film and characterize the film property.
Okay, I see. Well, maybe that was the case. And for my last questions, you mentioned about the self-healable material on the almost, and does this self-heal ability is remain the same when we have it under much reduced temperature?
Yes, I think an interesting question. So this self-healing is conducted at the room temperature. So under the room temperature. So it takes, for the thin film, like scratching, it takes like several minutes, like 10 minutes to completely self-heal. And for the freestanding film, like thick film, it can be self-heal like very quickly with the gentle press. But even though without pressing, it can self-heal within 2 hours. And then temperature will also affect the self-healing capability. So I think it is worth investigating the self-healing capability as a function of the temperature. But I didn't this kind of detailed study. Room temperature is fine to self-heal. But some of the self-healing material is only self-heal at high temperature, as you know, like 80, 90 degrees Celsius. Some polymer can shows the self-healing property, but it is not very common to have the self-healing property at the room temperature and without any kind of stimuli. So that is the one of the biggest achievement from my group.
All right. Thank you for your enlightenment. It's really nice to talk with you today.
Okay, thank you.
Thank you.
Okay, thank you for the question and also the and thank clear response and also answer from Professor Jun. And we still have one more question from Dr. Roto. Pak Roto, please, you could directly to ask to Professor John. You still join us? Pak Roto?
Yeah. Okay.
Yeah,
Thank you very much.
Please, you yeah. Okay.
Hello, Professor John.
Hello.
Yeah. Actually, I had experience synthesize the spinel of lithium manganese oxide and so on and so forth.
I see.
Even the cobalt also. But the problem that I had before is that when we try to understand the stability of the material using the X-ray diffraction, after we do the many cycling with the voltammetry, and then we lost the structure actually. The structure of the spinel is not intact. So that's the reason. Yeah, the reason of. I see. Do you have any idea how to maintain the spinel structure still there if you do the cycling, because the cathode material is so important? Yeah.
So lithium manganese oxide stability is less than lithium cobalt oxide. That is what you.
Yeah.
I see.
And cobalt is actually much better. You can see that's lithium cobalt oxide. It's much better. But what I did, if you cycle up to like 500 cycle and then it lost the structure, the spinel is lost, and then
I think
the battery is dead.
Right. So I remember.
You have any idea how to if you have experience maybe how to maintain the structure?
Manganese oxide, the decreased problem, like the capacity fade problem, is about coming from the dissolution of the manganese ion. So manganese ions can be dissolved during the cycling test. So if you can actually prevent that kind of dissolution of the ions by protecting the manganese ions, generally people use some of the coating, maybe polymer coating or the carbon coating. You can increase the cyclability, and another way is actually maybe doping with the heteroatoms.
I tried doping with nickel, but not that good. With nickel, I dope nickel, but it's not that stable either.
Nickel is also, nickel can provide a high stability, but stability of the nickel oxide is not high, right? So maybe
it's not high.
You better test like more strong the metals like zirconium or other metal would be, I think, better choice. For the cyclability, but as you mentioned, nickel is good for increasing the capacity. So
but not for the stability.
Yes,
not stability. And then another experience is that when you cycle like lithium manganese oxide, and you have also the phase separation. Sometimes you produce manganese oxide M2O3 or MNO and everything else that make the life is difficult.
I see.
After when we finish the cycling and then you take the material, you do the X-ray, and then you have so many phases. Not just spinel, but you could have a manganese oxide separated, and then manganese trioxide MN2O3, and so on and so forth. That's something that we actually
I see.
try to understand why so complicated when after you do the cycling process.
Between lithium, during the lithium intercalation, deintercalation, maybe crystal structure distorted and change it to the different structure.
Yeah, we also try to measure the bond, manganese oxygen bond during the cycling and changing. Yeah, using the X-ray.
Bond length.
Yeah, bond length. Yeah, bond length changing.
I see.
Yeah, sometimes bond length change, and then from the XPS data. From the XPS data, the oxidation state. Manganese oxide sometimes in between 2, 3, and then 4. This among the possible. Yeah. So the oxidation state is not 4 plus or 2 plus, but can be in between. Yeah, in between.
Right.
Yeah. That's
what voltage did you use for the cycling?
For cycling, we just use in the ethylene carbonate medium, and it's just using the normal voltammetry with electrolyte. Yeah.
So did you apply very high voltage or?
Yes, we try very high voltage. Yeah. So to understand if the material is still stable. Yeah. And then about the plasmonic that you did for the gold, you synthesized a cubic gold nanoparticle, right?
Yes.
How did you control that you have the only cubic? Sometimes we have a hexagonal, sometimes we have a spherical, and so on. But my curiosity is that how you control you can only have a cubic.
Yeah.
How did you did? How did you did together?
So
cubic.
Golden nanocube is usually can be synthesized by the seed mediated method. So there's some of the seed should be added into some of the solutions at the right timing and then right concentration. So there are a lot of recipes to synthesize golden nanocube and golden nanorod, but actually the researcher should practice. The student should practice. The morphology. This is like the little bit technique thing.
Yeah, sometimes we have a mixture, right? Cubic, hexagonal, and then sometimes spherical. But you have a nicely cubic, so that's what I want to learn. How?
Yeah, actually, we get some help from the other group members to have expertise in the.
Did you try to change the capping agent and then the reduction agent and so on?
Capping agent was I don't remember the exact. Yeah, some of the polymer I don't remember the name, but capping agent is the organic polymers.
Exactly, but sometimes we try to control it with the capping agent and the reducing agent. For example, you use citrate, sodium citrate, and like that. Yeah.
Right.
Okay.
Ascorbic acid.
Yeah. Ascorbic acid and citric acid.
I see.
Okay. Yeah, but to get a nicely like dispersed with one shape, let's say. That's sometimes we have to control so many things, like the precursor concentration. Also, you have to control it, right? The cold ion. Let's say you have started with the cold ion. And then actually one more question is about how did you assure that the shape of the plasmonic can be really reversible by just using the UV spectra?
So this one I repeated cycling many times.
Yeah, the cycling,
very stable, and CB is also very stable. So
it's stable,
After 100 cycles, it shows the same behavior. So we can this material core shell is very stable.
Yeah. So I assume that there is no change in the dielectric constant. And
dielectric constant. Refractive index is related to the dielectric constant. So this one is the dielectric constant change. So ES has the lowest one and LB is the high one. So if we convert this ES to LB and LB to ES, we can get the refractive index change of the material, and then it provides the the different refractive index environment.
Environment. Yeah.
Volt.
So the idea is it's a reversible. So it's nice if you can have such a like behavior. Maybe we can have another application in the future.
Right.
Yeah, as a sensor, for example.
Yes.
I'm doing the sensor using this also.
Oh, really?
But,
okay.
Yeah.
I see.
Yeah.
Good.
How to control the dielectric constant surface, because we don't want to change the dielectric constant during the use of nanoparticle for sensing. Otherwise, you get confused because it just change in the dielectric constant, but not change because the concentration of the analyte, the target molecule. Yeah.
Target molecule is the only molecule you want to detect.
Detect. Yeah. So we don't want to get mixed up with the change in the dielectric constant or refractive index.
I see.
Yeah.
Right.
Yeah. Okay. Thank you very much. Good talks,
Okay.
I think. Yeah.
Thank you for the question. Yeah.
Okay. Thank you. Thank you, Pak Lut.
Yeah. Thank you, Pak Roto, Dr. Roto, for the question and also discussion. Very useful for us and makes clear what the Professor Jeon has already presents. Okay, before we close the meeting or the seminar, I just also have one question, Prof. Jeon, about the organic polymer that we use for replacing the inorganic battery, especially lithium. And I think so far as I know that organic polymer has very low stability, and that way the cyclability is very low, and you have already modified and improved by using combination like penny and PEMSA, something like that, and then also what they call to create layer by layer by using other polymer. The question is, it is possible to improve the stability by forming like complex formation. For example, we modified with metal ion, something like that, and then if the polymer involved in the complex formation, maybe can improve the. Sorry, there is okay. Could you know what I mean?
I think it's very good idea. So very interesting thing to try. So organic material has its own disadvantage, and inorganic material has advantage but disadvantage also. So if you combine them together in the good way, I mean in the scientifically good way, maybe we can maximize the advantage and minimize the disadvantage of each material. So
this is also possible, but you haven't tried that.
Not yet.
Not yet. Yeah. Okay. We still have time. Maybe we have to stop 10:30. But if there is no question anymore, I have to stop. Is there any question from the audience?
Yeah, Professor Nuryono.
Pak Agus, okay.
Yeah. Thank you very much, Professor Jeon.
Okay.
You contacted me for the first time to our department, and thank you very much.
Thank you.
And you can continue the collaboration with Professor Nuryono. He is head of material research group.
Research group.
So this seminar can be conducted due to his group. And I have one question if we compare with you have a thin film that very stable as another high performance in lithium battery, and if you compare with the thin film, it is more okay or something, the same case, something like.
Okay, I understand your question. So usually for the battery electrode, the thickness is also very important factor. So for example, like thickness should be 50 micrometer and 100 micrometer to go to the commercial level. But in this technique, actually, unfortunately, cannot provide that kind of thickness. Only works in the thin film. That is the drawback of the this kind of approach. Yes, that is the very, I mean, the pinpoint question.
Okay.
But it should be. I mean, there should be some way to improve. But
Okay. Yeah.
Yeah.
Okay.
Thank you, Professor Jeon. Yeah.
Okay. Thank you, Pak Agus, Dr. Agus, for the question. I think this is the last question from Pak Agus. And once again, we would like to say thank you very much for the nice presentation, and also information from Professor Jeon to offer very good and very interesting scholarship. Maybe some of the participants would like to contact you directly, and maybe I hope that you will find best student and also excellent student from Indonesia and Yogyakarta especially. And this is one of alumni from Gajah Mada. Some of Gajah Mada alumni have already continue maybe master and also PhD, not only in South Korea, but also in another country like in Japan and also in Taiwan. Yeah, I think this is some of our achievement in the Department of Chemistry, Universitas Gajah Mada, or UGM. Okay, if there is no more about question and also discussion, so I have to stop this seminar. And thank you once again for June. And maybe before we stop, maybe Pak Adi, Mas Adi would like to take a photo together.
Yeah. Okay. Maybe please turn on your webcam for our participants. Please wait. Now it's still presentation from Prof. Jeon.
Prof. Jeon, could you stop your presentation?
Yeah, sure.
Yeah, that's good.
Okay, please wait.
Everybody want to make on the video. Pak Bu Eko. Yeah, maybe not only one time, because we have more than 80 participants in this platform, but also we have from another platform, YouTube, and also streaming.
Okay, 1, 2. Okay, maybe that's enough.
That's enough. Okay. Thank you very much for all participants, and also Prof. Jeon, and also Pak Agus as a head of Department of Chemistry, and also all participants from Gajah Mada and also from the alumni. And see you in the next seminar, and have a nice day, have a nice weekend, and also keep your health from the corona or COVID-19. See you. Bye-bye.
See you. Bye.
Bye-bye. Terima kasih Bapak Ibu semuanya yang sudah bergabung. Selamat berweekend, kemudian menjaga kesehatan. Salam sehat untuk kita semua. Dan akhir kata, wassalamualaikum warahmatullahi wabarakatuh. Dan ketemu pada pertemuan yang akan datang. Terima kasih, matur nuwun Mas Adi, bisa di off atau bisa diakhiri.
Terima kasih.
Oke, makasih semuanya.
Matur nuwun.
Ya, alhamdulillah Pak.